Hi, welcome to our very last set of chapter review questions for Discovering Design with Physics, chapter 16. Now, as I'm sure you've noticed, this chapter has no calculations in it. So this review question session is going to be pretty short because most of our time is usually spent doing calculation questions, and when the questions are easily found in the book reading, and I don't feel like it needs much more of an explanation, I don't give that to you, but I will point you in the right direction in case you are confused about any of the questions. I'll tell you where to look for the answers in this set. So, starting with question 1, there are a lot of definition questions, and we will cover none of them because, as usual, you know where to find them. For question 2, do magnets exert a force on stationary charges? What about moving charges? So there is a bit in the book that specifically, explicitly states this for both of these, and that's on page 425. So I'm directing you there for question 2. For question 3, do electric monopoles exist, and what about magnetic monopoles? The discussion for that can be found on page 426, so head there for that if you are confused at all. For number 4, we're asked what's wrong with the magnetic field lines drawn in each of the following diagrams. So rather than give you this answer, I'm going to direct you to that big pink box on page 427, which is that list of things that you should have memorized, some rules for magnetic field lines for this chapter. And then I'll also just point out this here, the diagram of the magnetic field lines of Earth. That is not on that page, but there is a correct diagram on page 431, and so you can look there to see what exactly is wrong with C here. For number 5, we have the magnetic field drawn here, and we're asked which pole is the South Pole? Using up and down, right and left, describe how the North Pole would point if placed at location A in the drawing. And then for C, which location would produce the most magnetic force on another magnet? So for this one, I'm directing you to page 427 also. In there, there's discussion about the direction of field lines and what they mean, what those forces are, what the closeness of the lines tells us about the magnitude of the force, which, hint, is a little bit similar to electric lines there, the electric field lines. If you're still a little bit confused, there is a very similar problem in the comprehension checks that you can refer back to, and it might help you out with that. For number 6, Maxwell's equation for the speed of light is given below. Suppose you measured the speed of light in 2 different media. The first one has higher electric permittivity and higher magnetic permeability than the other one. In which medium is the speed of light faster? So just remember that electric permittivity is this epsilon, and magnetic permeability is mu here. And so if you insert a larger number in the denominator, because both of these numbers are larger in A, what happens to the speed? Okay, and this is a pretty similar problem to several that we have had this year. Just thinking about if you change the number in the denominator, make it bigger, what happens to the overall value? And so if you don't know, insert a bigger number into the denominator versus a smaller number and see which one has a higher speed of light. For number 7, we need to draw the magnetic field line produced by the circuit on the right at point A. Okay, so with this, we're going to remember the right-hand rule, all right? When the electricity is moving this way, right, from the conventional, with conventional current, so it's got to be moving from the positive side to the negative, you're going to take your right hand and stick your thumb out and point your thumb in the direction of the current, that the conventional current is moving. Okay, so at A, it's pointing down. Okay, and then look at your fingers and what they are doing. They are curling to the left and under, and so that's exactly what is going to happen here. So it's going to be this way and then going under. And so just draw that as best you can with the three-dimensional drawing on a two-dimensional surface here. Okay, so on top is going left, and then it goes under here. For number 8, a bar is made with a ferromagnetic substance. If it is not a magnet, how would you make it a magnet? If it is already a magnet, what could you do so that it wouldn't act like a magnet anymore? So the discussion for this one is on pages 434 and 435, starting with the definition of ferromagnetic substances, and it describes pretty well how ferromagnetic substances can become magnetic or lose their magnetivity. For number 9, an object is attracted to a magnet but isn't acting as a magnet. What are the possible types of substances out of which it could be made? How could you determine which of these possibilities is correct? So for this one, you could go to the discussion on page 434, but I am going to go ahead and explain this one. So definitely cannot be diamagnetic. Diamagnetic substances will never be magnetic, but it could be paramagnetic or ferromagnetic, okay? Because both of those can be attracted to a magnet. How we could determine which of those is correct is that we would put it in a magnetic field. Okay, so a ferromagnetic substance, like we just talked about in question 8, would become a magnet after being removed from the field, and a paramagnetic substance would not. All right, so it's not acting as a magnet now, but if we put it in a magnetic field and it is ferromagnetic, it will become a magnet. Versus if it's paramagnetic, it would still not be acting as a magnet after being put in that magnetic field. For question 10, excluding solar power plants, how do power plants generate their electricity? What kind of current is produced as a result? So this one, again, I'm going to refer you to the book. We're going to look at pages 436 to 437. There is discussion on how electricity is made for homes there, and it goes over all the different types of power plants, excluding solar power plants in that section. And also tells us what kind of current is produced. For number 11, what is the main difference among coal power plants, gas power plants, hydroelectric power plants, wind power plants, and nuclear power plants? So this one, it's really in that same discussion. So I'm going to direct you to page 436. For 12, what are the differences between all of the power plants listed above and a solar power plant? Again, let's look at page 436 to 437. And if you haven't really gotten all of this from that section, at the bottom of page 438, there's more specific info on solar plants that might be helpful. For question 13, a light that needs 25 volts in order to turn on is hooked up to a standard American outlet. Will the light stay on continuously? Why or why not? So it needs 25 volts constantly, and if it's hooked up directly to an outlet, it will not stay on continuously. The voltage changes coming from an outlet. Remember, that's alternating current. And so when it dips below 25 volts, that light is going to stop working. Now, this frequency of this is very quick, and so you can't really see that with the naked eye. This actually happens with LED lights. They blink on and off as the voltage goes up and drops. However, the voltage changes so quickly, we don't notice it. For number 14, what is the difference between the voltage at which an electric outlet is rated and the maximum voltage it produces? So if you remember, there's a term in the book called the RMS, which stands for root mean square. And so the rating of the outlet is actually this and not the maximum. And so if we were to draw this out, I'll draw a little chart here. Okay, so here's 0, and our alternating current is positive and negative. And it should be approximately the same amount up and down each way, and absolute value on either side is the same. So forgive my drawing that it doesn't look perfect. Okay, so the maximum value is here, right? And let's pretend that all of these go up to the same maximum value. Okay, so this is max. But the root mean square is not there. It is around here. Okay. And so the maximum voltage of any outlet is going to in fact be higher than what the rating is for that outlet. For question 15, suppose a device requires direct current in order to work. What must be put between the device and the plug if it's going to be powered by the electricity from a wall socket? So for this one, I'm going to refer you to the discussion on page 438. And finally, 16, a constant force is used to make a magnet move through a pipe. Compare the magnet's acceleration in a pipe made of an insulator to its acceleration in a pipe made of a conductor. So if you did experiment 16.3, you saw what happens in this situation. But if you didn't, there is the discussion before and after that experiment that you can read that will give you the answer to this question. And that is it. We have reached the end of Discovering Design with Physics, minus whatever exams you still need to take. I hope that you've had a great year as I have, and I hope that these videos have helped you get through this year. Good luck on whatever your future endeavors entail.